Now we're going to discuss an example where we are going to go through how to compare two regression lines. And the topic that we'll be discussing, the context, is the production of flowers. So we've got these seedlings. Each experimental unit is a group of 10 seedlings, and the seedlings are exposed to different intensity of light and also different timing of light. So there's early timing and then late timing. And we're interested in how do these two factors, or two variables, the timing of the light and the intensity of the light, affect flower production, our response. The first thing we'll do, so let's see, let me just write this out so that it's clear. So y equals the average number of flowers from 10 plants. And we have our x is light intensity. And you can think about it, we did this experiment where we did light intensity early and light intensity late. So there was this treatment which is the light timing, either early or late. So there are two groups. It's going to be binary. If you look over here, you can see the data subset for the early light treatment. So we have 12 observations, and the number of flowers is here, the average number of flowers from our 12 seedlings. The time is all E for early, and then these are the different intensity values. We can fit a simple linear regression where our model is, so for early, we can fit the model y equals beta naught plus beta 1 times x plus epsilon. Okay, this is our model for the early light, and we get estimates for the intercept. So this would be here. This is 71.6, and beta 1 hat, our estimate for the slope, or the relationship between how number of flowers changes with a 1 unit change in light intensity, is pretty small, negative 0.04. Okay. Well, I guess the units of light intensity are large, so maybe it's not small. Standard error is also small. Both of these are significant. So that means we have a clear, the intercept is clearly different than 0, and the intensity, the effective intensity is also clearly different than 0. Okay. For the late light treatment, let's go with different color for late. For the late light treatment, so the plants that get the light late, we have a similar model, right? Let's go ahead and add an additional subscript here. So we'll use L to distinguish between early and late. We'll put some E's here. Alright, so hopefully that makes sense to you guys. I'm just going to add an E to indicate that this is the early and this is the late, the L for late. So when we fit this model, here are the data. This looks the same structure as before. We fit this regression and we subset down to where time is late. We find that the intercept, so our estimate for the intercept, so beta naught L hat is equal to 83.1. And we find that the estimate for the slope, beta 1 L hat, is equal to negative 0.039. So actually that rounds to 0. I'm just going to round to 4 here, just 2 significant digits. So you can see that the slope looks pretty similar, but the intercepts are different. And if we plot the data, this is what we see. So the early line is in black here, and it's lower. And the late line is in red, and it's higher. And we can see that the lines look quite parallel, and that's because the slopes are the same. But there's a shift of, looks like about 12 between the intercept for early and late intensity. So late has more flowers produced at a given intensity. Okay, so our question then is, how do we compare these lines? How do we compare these lines in some kind of systematic way? How do we do a test for, are these lines the same? Now the slopes look like they're the same, and the intercepts look like they're different. But how can we actually use statistics to test for that? Well, we're going to use the approach that we talked about in the previous video. We'll use qualitative variables. So, again, our question is the relationship between intensity and flower production the same for both groups, meaning the early and the late flowering? Are the slopes the same? Are the intercepts the same? That's what we're interested in. So to do this, let's define some new variables. Okay. So let's call x1 is x up here, which is light intensity. Let's say that x2 is equal to 0 if we've got late, the light treatment is late, and 1 if the light treatment is early. And then we'll define a third variable, x3, as product of x1 and x2. So x1 times x2. And then we're going to fit a model, y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Alright, so if we're dealing with the early case, which is blue, so we're talking early here, what will the model become? So we've got, let's do it this directly under, y equals beta naught plus beta 1 times, so if it's early, x1 is 1, so it's always 1, plus beta 2 times x2, oh, sorry, I screwed that up, out of order. So x1 is light intensity, right? So that varies, x1, plus beta 2 times x2. Now x2, if it's early, is a 1, plus beta 3. And beta 3, right, is x1 times x2. Sorry, I need the 3 here. So if it's early, x2 is always 1. And so 1 times x1 is just x1. This simplifies to beta naught plus, beta naught plus beta 2 plus beta 1 plus beta 3 times x1 plus epsilon. I rearranged the variables a little bit, so you can see that these two are going to make up our intercept, and these two are going to make up our slope for light intensity, x1. If we have the late case, so late light treatment, y equals beta naught plus beta 1, x1 plus beta 2 times 0, because x2 is 0 if we're in the late case, plus beta 3 times 0. Because if we're late, x2 is always 0, 0 times x1 is always 0, so it's 0 plus epsilon. And so this late line simplifies just to beta naught plus beta 1 x1 plus epsilon. So notice that these guys, the intercept and beta 1 for this model is basically the equation for the late. And for early, we have to add beta 2 to get the intercept to beta naught. And for the slope, we add beta 1 and beta 3. So beta 3 is the difference in the slopes, and beta 2 is the difference in the intercepts. So if these lines are the same, beta 2 should be 0, and beta 3 should also be 0. Let's take a look at what these are. So in R here, we've recoded things. So early is 1 and late is 0. And we add an extra column for time times intensity. That's this x3 here. So we have the number of flowers, our response. We have time, which is either early or late. Again, it's been recoded 1 or 0. We have intensity, which we had before. And then time times intensity. So for the top part of this, you'll see that the values are basically, they're just the values of intensity. But for the second half of this data frame, where time is 0, time times intensity is also 0. So we'll fit this full model here. Flowers tilde intensity plus time times intensity. That's this full model right here. And let's look at what the coefficients we get are. So let's try to get our estimates here. So what's our estimate for beta naught hat? So our estimate for beta naught, that's why it has the hat on it. That is here. It's 83.1. What's our estimate for beta 1? So beta 1 hat. Beta 1 hat, okay, so beta 1, that was times x1, and x1 was light intensity. So that's this coefficient here. And, whoa, Willis. That is negative 0.039. So we're just going to round again to 4, like we had before. And then let's do beta 2 hat. So that would be time. x2 was time. And that's negative 11.5. And then beta 3 hat is negative 0.001. Okay, let's take a quick look at our previous estimates. So first, just beta naught and beta 1, right? Those are the coefficients for the late model. And we have 83 and negative 0.04. 83 and negative 0.04. So we've actually fit the late model right here. These are the estimates for the late model. It's exactly the same as when we fit it separately. That's kind of a cool thing. So you can fit this model like this. You're actually fitting both lines at the same time, and you can recover the exact same coefficient estimates. Now let's look at the estimates for the early model. So the intercept for the early model is beta naught plus beta 2. So beta naught is 83.1 and beta 2 is 11.5. Add these together and you're going to get, let's see, 71.6 or so. So let's look at that for the early model. Yep, 71.6. That's our estimate for the intercept for the early model. And you can see that the slope is 0.04, which if we subtract from beta 1, or sorry, if we add beta 1 and beta 3 to a rounding error, we're going to get the same answer, right? Because beta 3 is so small, it's 0.001. So it's just a very, very slight change. So this is making sense. So what we've just demonstrated is that we can fit the model like this and actually recover the two separate lines the way we fit them before. Now, what we can also do is we can ask some interesting questions. So let's go about doing that. We might have some hypotheses that we want to test, right? I'm going to make a little table here. Hypothesis. So we might have a hypothesis, let's see, HO, beta 3 equal to 0, given beta naught, beta 1, beta 2. What is the interpretation of this? So do they have the same slope with varying intercepts? Let's take a look at that. So beta 3 right here, right? Beta 3 is the difference between the slopes of the early and late, the slope with regard to light intensity. So if beta 3 is 0, that means that the slopes are the same, right? Now we have beta 2 given here, so that means that we're allowing the intercepts to vary. So that's what I mean by with varying intercepts. What if we have, let's say we want to do same intercepts with varying slopes? You still want to say, do our two lines have the same intercepts while we allow for their slopes to vary? What would that hypothesis look like? Okay, so what is the parameter that is the difference in their slopes? I'm sorry, difference in their intercepts. The difference in their intercepts is beta 2. Alright, beta 2, this 11.5, that's the difference in their intercepts. So to test if the intercepts are the same, we want to say, is beta 2 equal to 0, given beta naught, beta 1, and beta 3. If we were to drop beta 3 from this, we would be not allowing the intercepts to vary. We say, do they have the same intercepts, assuming that the slopes are the same. While having beta 3 in here, we're allowing the slopes to differ. Let's go ahead and get the p-values for these hypotheses. Okay, so notice that this is a hypothesis about a coefficient given everything else is in the model. And so is this one here. So where should we look from our R output to find the p-value for this hypothesis? From the summary table. The summary table gives us the t-test, right? Which tells us, test the hypothesis. Is this coefficient equal to 0 given all the other parameters in the model? So beta 3, this is the coefficient for time times intensity, the interaction between time, early or late, and intensity. And you can see that the p-value is 0.9, so it's super high. Might have been going to write the rest. It's point high, 0.9, very high. So there doesn't seem to be any evidence that it's different than 0. So it seems like it's reasonable to accept that they do have the same slope. What about this hypothesis? Is beta 2 equal to 0 given everything else? Beta 2, let's see, beta 2 here is the difference in the intercepts. And that's going to come from here, this time, because this is our binary indicator variable. And the difference is negative 11.5, right? And let's look at this p-value. The p-value here is borderline. It's much smaller, not super small, it's 0.075. So maybe there's something going on here. Now, what's notable though is that we're testing for, are the intercepts the same while allowing the slopes to differ, right? But we don't have reason to think that the slopes really differ. So can we test the hypothesis, do these have the same intercepts with not varying slopes? Or with having slopes that are the same. And by slopes, again, I mean the effect of intensity on balloons. That would be the slope there. So here, this hypothesis, again, we're going to be dealing with beta 2 because we're talking about intercepts, differences in intercepts, but we're not going to have beta 3 be given in the model, okay? So it's basically we're dropping that interaction term from the model. So how could we get this p-value, the p-value for this test? Well, remember that when you fit the model and then you call Anova on it, it gives you the sequential sums of squares table. And because the interaction term, so x3, comes after x2, we can use the Anova table to test this hypothesis. So this row in this Anova table corresponds to this hypothesis here because the interaction time intensity, which corresponds to beta 3, that's after time. So this corresponds to this hypothesis, this row here. And the p-value here is super small, so it's 0.0002. So it seems like there is very strong evidence to think that the intercepts are different, which conforms to what we saw when we plotted the data. So you can also construct these tests using the additional sums of squares, where you could fit the reduced and fit the full model and then call Anova on them to test for differences. That example is here, where we have a reduced model, and the reduced model has intensity and time, so it doesn't have the interaction between time and intensity. So this model corresponds to changing, varying intercepts, but not varying slopes. So we fit this model here, and then we call Anova on this reduced model versus the full model, and we get the p-value 0.9096, which is this same p-value up here, because this model, when reduced, is this model, and the full model is the full model where we have all of them, so we would get the same p-value. So it's the very same test. So this test here done with the additional sums of squares test is the same as this test here. Okay. There's a lot of stuff, and I hope that it makes sense to you. It does take a little bit of time to sit down to really understand these things. I don't think... There's a good chance that maybe you glossed over you, or maybe since you couldn't raise your hand and say, whoa, I got confused about that, or you misspoke, you couldn't interrupt and ask a question. So you might need to rewatch it. If I did misspeak or I said something confusing, please post to Piazza. I think there's a fair bit going on here where you have to not only understand sort of the algebra of how these models work, why they're working the way they are, how to set up the hypotheses to test the particular questions you're interested in, but then also how to get that out from R. So there's a number of kind of moving parts. So please don't hesitate to ask a question. I fully expect there to be questions. Just to summarize or finally discuss, we should also check assumptions for our model, which you can do here. We can look at the residuals versus fitted, or what's called predicted here. There doesn't appear to be any pattern, no increasing variance or anything like that, no pattern, and that the QQ plot looks pretty good. So the model assumptions appear to be met, and they, as far as we know, the data are independent of one another.